Excellent. Cool. 2:35. I think we can get started. I'm observing a bias. Like all of you, most of you are sitting closer to the doors. Is it like as an exit plan? Like in case something, in case the lecture gets too boring. Also, some of you kindly let me know that you have to leave at 1 hour in, as you did last time, very silently, which I greatly appreciated. Thanks for letting me know. That's very kind of you. That's obviously not a problem at all. Cool. So today we're going to have the second kind of, I guess, notation intense lecture. I mean, I guess the math isn't super complicated, but it's like, it's just kind of a lot. So I actually appreciate that after hearing the first lecture, you're coming for this second lecture, even though I warned you that this one is going to be the same as the previous one. Starting from this one, though, like starting from next time, that's over. So then all the fun stuff starts. So like this is the kind of the basics. Cool. So today we're talking about multiview geometry. It is a recap from last time. Last time we talked about homogeneous coordinates. I hope everyone remembers that. We said we also introduced some notation. We said, well, we have like small case letters are usually pixel coordinates, and we have R2, which is just 2D coordinates, and we can turn it into homogeneous coordinates by appending a scalar 1, making it into an x tilde. That's the homogeneous coordinate, and then we introduced this way of converting them again. And then in 3D, it's the same, just with 3D, obviously. And we used this homogeneous coordinates to conveniently introduce a set of matrices that are the convention of denoting camera parameters, namely the camera pose and the camera intrinsic parameters. We introduced this world to cam matrix here, which basically takes a 3D homogeneous world coordinate, takes it to 3D camera coordinates, and we have this. We introduced this intrinsics matrix here, which takes a 3D coordinate in camera coordinates. So it's a coordinate that is expressed in the camera coordinate frame and maps it to homogeneous pixel coordinates. And again, from homogeneous pixel coordinates, if you want the actual pixel coordinates, you have to convert it into a heterogeneous coordinate. So then you have to do this divide by W, right? Were there any questions on that exciting topic? No, excellent. Great, then we're moving on. This was called the world to cam matrix, world to camera coordinates. This was called the intrinsics matrix K. Actually, this 3x3 subsection of the matrix is called the intrinsics matrix, and then we have this awkward little operator here that takes it from a 4x3 matrix to a 3x3 matrix. Sorry, 3x4 matrix to a 3x3 matrix, right? Okay, and so the whole term for projecting something, which we're going to rely on heavily today, is looking like this. So we basically have a pixel coordinate here, we have a world coordinate here. First, get it into camera coordinates with world to cam. So just for the record, again, that basically means you have like a world coordinate frame somewhere you pick. You have a camera that's looking at something. You have a 3D coordinate somewhere. So first step is you have to transform this point into the camera coordinates. That's the job of the world to camera matrix. And then you project it onto the camera coordinate frame, onto the pixel coordinates that with the intrinsics matrix. And then you have to do the z divide to take it into heterogeneous coordinates. Great, fantastic. So then last time you were a witness of like a funny occurrence, which is that I had put something on the slides, which I derived last year, but then forgot about and just assumed that I could rederive it here in the lecture, which I couldn't. The thing that we're going to do that again now, very briefly. So the thing that I got confused about yesterday on the slides, or like the Tuesday on the slides, was I looked at this equation and I forgot what the px and py were, because there is a convention where the px and py are oftentimes the pixel coordinates. But just as a reminder, the px and py are not the pixel coordinates. They are the position of the image center, right? So they are the offset that you add to the image coordinates. So let's go through this little equation again here. So this is the derivation of the unprojecting operator. So if you have a point in pixel coordinates and you have its depth, what is the 3D coordinate of that point in camera coordinates? That's what we're going to derive. And I already gave you the intuition last time. It's like intuitively, right? You have this linear operator, which is the intrinsics matrix, which takes you from a 3D point to a 2D pixel. Intuitively, the inverse of that should be something that takes you from 2D pixel coordinates to 3D. The only kind of weird thing is that the intrinsics matrix takes the depth away, right? It kind of like the pixel coordinates are 2D and they lack the depth, and so there is like the question of how do you deal with the depth. We assume that you have to. Okay, so we're going to derive it now. It's actually completely straightforward. Okay, you have an XYZ world coordinate here. You have the intrinsics matrix K here. For the record, intrinsics is F, Px, Py, 1, right? And then you just multiply out the right side, and then that's what pops out on the left side, right? So the X is multiplied with F, the Y is multiplied with F, and then you get both times Z times Px, C times Py, and on the bottom you get Z. Does it make sense? Can you imagine that? I should have written it out. Yeah, okay, good. Then, and now you just crunch numbers around. So what we want in the end is, right, we want to end up with a 3D coordinate in world, we want to end up with a 3D coordinate in camera coordinates, right? So we multiply with the inverse of K, takes us to this, right? Nothing changed except for inverse of K. Now we can pull out the Z, right? Here we just factor out the Z. And when we pull out the Z, what we have here is Z times K inverse times F times X over Z plus Px. And it just so happens, this is where I got confused. I thought Px, Py, I was like, these are the pixel coordinates, doesn't make any sense. But they're not the pixel coordinates, they're just Px, Py from the intrinsics matrix. And it turns out that is exactly X pix and Y pix, right? So this whole term here is the Y pixel coordinate. And so then you have derived this, right? This is a bold X, so this means this is now a 3D coordinate that you have expressed in terms of the homogeneous pixel coordinate and the depth. Does that make sense? So this is now the unprojection operator. It's refreshingly simple. This is how you might actually, like, I think I've literally tens of times written a function that has exactly the signature. It takes like a pixel coordinate as input and a Z depth, and then it gives you the thing. Cool. That's it. Beautiful. Does that make sense? Good. Just wanted to revisit that after screwing it up last time. So now we're going to talk about multiview geometry. So why do we care about multiview geometry? We want to understand how to reconstruct the 3D world from 2D images. And as we discussed last time already, doing that, you can do it to a degree from a single image, as we'll see like a little bit later in the course. It is possible. But if you do it from a single image, it's all learning based, right? Like in a single image, there is no 3D information. If I just gave you a single image and you didn't know anything about the world, you wouldn't know anything about the 3D scene depicted in the image. But the moment you have many images and you know the geometry of the system, it turns out you can reconstruct the 3D world, even without any machine learning whatsoever. And this is, in fact, what this paper here was about. This paper is, I think, phototourism. This is written by Noah Snavely. He's at Google and Cornell Tech. And this was a paper where back in the day where Tumblr was still a thing, he scraped all of these images from Tumblr. I think it was 2007. And then he ran one of the algorithms that we're going to discuss in class today on it. And that was able to reconstruct the camera positions and the camera intrinsics parameters as well, plus the point cloud. This is a classic algorithm. There's no machine learning in there. But it turns out the same techniques are essential to the state of the research today. In fact, some of the research that we're doing today in my research group are thinking about like new ways of doing this that actually do profit from deep learning. So this is very exciting. So let's do this. Again, here's the people that some of the slides were adapted from. You can go back and look at their slides if you want to delve into any of these topics more deeply. Okay, so here's actually the input-output behavior that we're looking at today. I give you a video like this, which is actually a video from a data set called Real Estate 10K. Happens to be also from Noah, who is the guy who wrote this other paper. And so this is like a boring video, of course, it's like someone's kitchen, not that exciting. But given this video, it should be possible to reconstruct the poses of the cameras, the camera intrinsics, which is like the intrinsic parameters, and the 3D geometry of the scene, just from this video. and no machine learning, no nothing. And it's actually quite impressive if you think about it, right? Like if you think about, you have no trouble doing this, right? I can watch this video and I know how the camera moved, and you all know it, but try to figure out how you come to that conclusion and like where you know it from, like no idea, right? It's like, it's just something you intuitively do. We do it all the time intuitively. And one other thing to think about here is who plays 3D video games or has ever played a 3D video game? Good, most people. So think about this for a moment. It's totally crazy. All of us know that depth perception happens from stereo vision, right? That's something we grew up. But when you play a video game, you look at the screen, and on the screen there's like maybe someone's running around, and you actually just see the 2D image, right? You just see the 2D projection of the 3D world. You don't have any stereo information. The only thing that you get is actually this. You only get motion on the screen, nothing else. No depth cues, nothing else but motion and like pretty pictures. And that is enough for your brain to connect the input that you have to the little figure that is running around in the 3D world, which is actually fascinating. And we don't have anything that can do that right now. Like we can't have it be, this is actually an interesting research question. So just something to reflect on. So we'll do some progress on this today. So here's the topics of today's class. We're going to talk about triangulation, how to compute 3D locations if point correspondences. So we assume we have several cameras. Triangulation is we have point correspondences, so we know which pixels correspond to the same 3D point in the scene. If we know that, then figuring out the 3D geometry's point correspondence is triangulation. Then we have epipolar lines. So if you have a pixel coordinate in one camera and you know the pose relative to another camera, then can you figure out which pixels on the other camera could possibly correspond to, well, we'll talk about it. It's much clearer in images, I promise. Epipolar lines and epipolar geometry. Fundamental and essential matrices, that one doesn't make sense to explain until we get there. Then there's going to be a bunch of stuff we won't talk about, although it's very exciting. Then there's going to be bundle adjustment, which we can only dip our tiny pinky toe into. It's way too complicated, or it's like way too complicated for, like some people have literally a whole course on bundle adjustment. And then there's a question, what has changed since deep learning? In the last lecture, like last time I gave this course, I had added some slides because I was talking too fast. So this time I'm going to talk slower. And actually this, I pulled out into like a new lecture, which is actually very exciting, so the next lecture will be complete new content, which didn't exist last year, and it's actually very exciting. But what has changed since deep learning? Newsflash, not much, which is kind of nuts. Cool, and one thing that I want to address, who of you has taken the computer vision class? Damn, that's a lot of people. Okay, so to you, this content will seem familiar. I'm even more impressive that you're coming to the lecture because you must have noticed that the last lecture was the same lecture that I gave in the computer vision class. This lecture is also the same that I gave in the computer vision class. After that, none of the lectures will overlap anymore. See, I'm in a pickle because if I wouldn't teach these two lectures, then all of the people who just didn't raise their hand would be completely lost. So I have to teach it again. I hope maybe the second time you hear it, maybe the first time you hear it, it wasn't obvious. Maybe the second time you hear it, it totally sticks. And maybe you not run into any bugs anymore with multiview geometry, which is unlikely, but we'll try our best. Okay, so there are some papers that just came out recently, like a year ago, that use concepts that we're going to talk about in the class, the 8-point algorithm for inductive bias for relative post-prediction by VITs. David Fuhey, Justin Johnson, Chris Rockwell. Then there's this paper by Andrew Zisserman, input level inductive biases for 3D reconstruction, which you're going to talk about in the next lecture. Andrew, in fact, is the person who, together with Rick Hartley, did all of this fancy formalism that we discussed in the last lecture. So all of the stuff about intrinsics, extrinsics matrix, that's all from his book. So Andrew is still around. He's still doing great research. He's at DeepMind and at Oxford. And Ethan is now at Stanford, actually. So no, she just started her faculty position. So she just started a faculty position at the National University of Singapore, so the first author. So these people are doing really cool stuff. Then there's generalizable patch-based neural rendering, which we're also going to talk about later in the course. BARF, bundle adjusting neural radiance fields. Wei Chu, I just literally today sat in his PhD defense here at MIT. So he just graduated. He's Dr. Wei Chu Ma now. And this was one of the papers he talked about in his PhD defense. And it's using things that we're going to discuss, or like it's addressing things that we're discussing today in the lecture. Just to show relevance. So this all happened last year, basically, the last 2 years. Okay, good. We got that out of the way. Let's start with the topic of triangulation. So let's say this is Antonius' old office, as I told you last time. let's say this was taken from 2 cameras. Assume that we know the camera poses. So actually, this is a little bit confusing. I said known P1, P2. This kind of assumes that there's a world coordinate frame, right? And we have the camera poses of these both cameras relative to the world coordinate frame. If you only have 2 cameras, you could also say we attach the world coordinate frame to this camera, and then there's just one relative pose relative to the other camera. And in that case, one of these P1s, the world2cam matrix, would be an identity matrix. So just for the record. Cool. So let's say we identify, I give you the pixel coordinates of the same 3D point in these 2 images. So we have this x1, x2. So I tell you this is the same 3D coordinate, which is itself not a straightforward problem. But let's assume I gave you that. Now comes triangulation. So we want to compute the depth of that point. And you might notice, well, last time we already talked about this system here, and you might ask what is different from this system, because that's exactly what we did, isn't it? No, it's not, because in this system, we assumed that the cameras were both pointing forwards, and they were on the same, they were both pointing in the same direction. It might not seem like much, but the fact that the cameras are not pointing in the same direction, now they're like that, for instance, makes the problem a whole lot harder. So now we're talking about the general triangulation problem, the general problem of getting the depth of this point from 2 pixel coordinates. This is what a general stereo system looks like. So these are, well, it looks a little bit symmetric. I wouldn't put them at like 90-degree angle. Like imagine it's like a little skew. But like this is what a general stereo system looks like. So we have 2 images, and I tell you up front, these x1, x2, they belong to the same 3D world coordinate. So this is camera 1 with matrix P1, camera 2 with matrix P2. I hope you remember what P means. And now we're going to do triangulation. What does triangulation mean? We want to figure out the 3D coordinate that belongs to these 2 points. So the first question I'm going to ask, which set of 3D points map to the pixel coordinate x1? So I know that at least half of you must know the answer to this because you saw this lecture before. So what is the set of 3D points that maps to this pixel coordinate x1 in this 3D space? What's the set of? Cairo. Correct. Everything along the ray that goes from the camera origin to this pixel, any of these points map to this pixel coordinate. Does that make sense? Okay, second question. This is new from last year's lecture, so all of you have an excuse for not knowing this, but we just talked about it. How would you get that ray? How would you get that ray that takes you from the pixel coordinates to the 3D coordinates that lie on that ray? I'm going to give you a hint. This was the thing that I had forgotten last time. Yes? Correct, right? So we have a pixel coordinate now, and now we want to get the set of 3D coordinates that lie on that line. So that's exactly what the intrinsics matrix does. So the intrinsics matrix, there's actually, this gives you the set of points that lie on this 3D line in camera coordinates, right? If you are in the coordinate frame of this camera. So if the origin is here, then K inverse x1 homogeneous gives you this line, right? And remember, if you now multiply this with z, if you multiply this with some depth z, then that will give you the x by z coordinate of that point along that, according to that depth, right? Does that make sense? I need to see someone nod. Okay, you nod. That's good. Actually, like here's another funny little question. What if you, so K inverse x1, is that a unit vector? Or is it a vector that is not a unit vector? Guess it's a 50-50 chance. Yes? Right. It need not be a unit vector, right? So it's not a unit vector necessarily. So here's a, so calling this local ray direction, I just want to point out that this is not a unit vector. It's a direction that is not normalized. And you know that must be true because when you multiply it with the depth, right, it gives you a point that is the xyz coordinate of that point in camera coordinates. And if it were a unit vector, right, then it wouldn't give you the correct depth because of this little picture we drew last time, right? Remember, I told you this little thing, and I told you this is not the depth. This thing is the depth. Anyways, okay. Good, just quizzing to make sure everyone's still awake. Nice. So how can you compute this ray? We just discussed it. Great. So this is called an unprojection or back projection. There's like different ways of calling it. Good. Great. Okay, so now we're going to, this is not necessary. Good. Here's the math for what to do if the point is not in, if the origin is not at the camera origin, right? Then you also have to account for the rotation and the translation of the camera, right? Remember now, this O1 we say is the camera origin, so this is going to be like the translation of the camera. Then there's this R cam to world. This is the rotation matrix that takes you from a point in camera coordinates to a point of world coordinates, and so you have to go through the whole matrix P in order to get the lines along that, the points along that line. Does that kind of make sense? We can also talk about it in more detail, but I think you can, yeah, nod, no. Okay, you asked me if you don't get it. Perfect, good. So this is how you can get this line. Now, how do we find the exact point on the ray? Well, we're going to build the same line from the other ray, right? So like, and clearly the two lines should intersect at the correct 3D coordinate, right? And that is how you would find the 3D coordinate. It is hence called triangulation because it's forming a triangle. The kind of problem is that the lines usually do not exactly intersect, right? And that's because, let's say there's a little bit of noise in your camera. Any tiny amount of noise, could be discretization noise, could be any kind of noise, will lead to these lines not perfectly intersecting. And if the two lines don't intersect, then what would we do to find the 3D coordinate? We would have to solve a little optimization problem. So then we would be looking for the point along one of the lines that is closest to the other line. Or some other way, there's several ways of posing this optimization problem. So triangulation then becomes this problem. I give you a set of noisy matched pixel coordinates. This is general. It doesn't have to be 2 cameras. It could be 5 cameras. And you want to estimate the 3D point that they all look at. So you're going to build the projection of the 3D coordinate onto the ith camera like this, right? So just again, for the record, homogeneous 3D coordinate, world to camera, gets it into camera coordinates, intrinsics projects it into a pixel coordinate, and then you can, for instance, solve this little optimization problem that says, I want this projection of the 3D coordinate to be close to the correspondence that I had, and that's one way of finding, of solving this little optimization problem. Make sense? Great. Maybe this was actually already a triangulation done. So this is as much as we're going to talk about it. You can solve this with gradient descent or like some other smarter algorithm. Good. So the next problem, let's say I give you again the camera matrices for the two cameras, but now I ask you a slightly different question. I give you a point in one coordinate frame, and now I ask you, where would you look in this image to find the corresponding point in this image? And so now, of course, as a human, maybe this is like a little bit contrived. I've tried to motivate this with this intuitive example. It's a little bit contrived because as a human, you look at the image and you look at the other image, you're like, that's the same point. But in an algorithm, that's not that easy, right? That's kind of, that is what we're trying to build. Unfortunately, we can't start with that. So in an algorithm, it's a slightly more complicated problem. So where would you look in the image number 2? So of course, you could look at every pixel, right? You could like try to, I don't know, here's an example. You take that color there and you match it to every pixel in the other image, and then you like get a set of candidates, right? So in fact, that wouldn't work at all. But you could get slightly smarter. Instead of just taking the color, maybe you take a slightly more complicated descriptor and you match it to every possible pixel. It turns out you don't have to look at all the pixels. Instead, what you have to look at is the epipolar line. What's the epipolar line? That's built, again, a little stereo system. We have a 3D coordinate. We have the two cameras with origins O1, O2. This line here is called the baseline. This terminology is identical to the simple stereo system that we discussed in the last class. So if you have two cameras, the distance of the camera origins is usually referred to as the baseline. And now we are going to introduce some names. One term is going to be the epipole. What is the epipole? The epipole is the projection of one camera origin onto the image plane of the other camera origin. So in other words, imagine that I would have one camera that sees the other camera. Like, think about pinhole cameras, right? Like, it gets a little bit harder to imagine with iPhones, but imagine pinhole cameras. So you have a little box, there's a hole, and now I have one pinhole camera that looks in this direction, and there's another pinhole camera here. That pinhole camera has a center, and that center will fall somewhere onto the image plane of the camera that is myself, and that's called the epipole. So it's the pixel coordinate where the other camera origin projects to. And then we are going to call this the epipolar plane. So that's the plane that, well, where all of the 3D coordinate plus the two camera origins lie in. And then we're going to call these two things here the epipolar lines. So the epipolar lines, and now you might already see where this is going. The epipolar lines are the intersections of this epipolar plane and the image plane. And it turns out that if you have a pixel in the image x1. So I give you pixel x1, and I ask you, where do you have to look in image number 2 to find the corresponding pixel? It turns out you only have to look in the epipolar line, which makes sense, right? So in other words, the epipolar line, you can think about the epipolar line as the projection of the ray that goes through the pixel onto the other image plane. That is also a line in 2D, and the corresponding point has to lie somewhere along that line. Make sense? Excellent. Cool. So let's think about a few systems and where the epipoles are and what the epipolar lines look like. So here's two cameras that are converging. So which means they are looking like in the, how would you describe converging? Like the point that they're looking at lies between the two cameras. Okay, so that makes sense. So and what do the epipolar lines look like? They look like this. So if you take a ray and you project it onto the other plane, it looks like this, and you can see exactly this property that if you take this point here, and now you look at the epipolar line of this point in the other image, the epipolar line will look like that, and you can tell that the corresponding point lies on that epipolar line. And this is in fact a great way of debugging if your camera coordinates are correct and stuff like that. So that's what we always do. We do a number of things because you need a number of things because the bug is always somewhere where you don't expect it. But usually we start with like, oh, let's plot all the epipolar lines and make sure that the same 3D point in all the images lies on this correct epipolar line. That's always a good start. Okay, where's the epipole? So where is the projection of that camera origin onto this image? It lies like somewhere over here. The epipole, as you can, all the epipolar lines go through the epipole. So you can always tell where like the epipolar lines converge. That's where the epipole lies. Okay, you have parallel cameras. Then you can imagine that the rays are like going like that. If you project them onto the other plane, the rays will be exactly parallel to the image plane. So in this case, the epipole will just lie at infinity. So the epipole can't be really found. Okay, just for some intuition. Okay, and now you actually already know one way of computing the epipolar line. Some scary math here, but it's actually pretty straightforward, right? Like it's a line, so a line is defined by 2 points. So there's an interesting relationship, right? So the epipolar line in 2D is corresponding to a ray in 3D. So we already discussed how you can construct this ray. One of the coordinates is the origin of the camera. The other one you can get via this little unprojection operator. You just pick a random point along the ray, you unproject it, you get the second point, that gives you the 3D line. And now, of course, you can just go ahead and you can project these 2 points onto the image plane. You can take these 2 points, you project it onto the image plane of the other camera, and now you have the epipolar line, because the epipolar line goes through both these points. Nice, easy. Here's another example of epipolar lines on a real-world scene. And you can see exactly the same thing again. So here we have a 3D coordinate, and for this point here, the epipolar line is this. And as you can tell, the corresponding point, again, lies on the epipolar line. Any questions so far? This is just the third time I'm giving this lecture. I must admit it's getting easier. That's good. Cool. So some papers where epipolar lines appear. There's this paper, Generalized Patch-Based Neural Rendering. And who'd have thought? The thing that you're seeing here are epipolar lines. So this is the teaser of this paper. This is a CVPR paper from 2022, 2021 maybe, not sure. And as you can tell, so here's an image, and now they said, okay, we're looking at this point. Let's compute the epipolar lines in these other 2 images, and these are the epipolar lines that you can plot. And it turns, you might get an idea for what this paper does. This paper is concerned with novel view synthesis. So you want to render novel views. We're going to talk about that later in the course, but imagine I tasked you with this task. I give you these 3 images, and now I want you to render a novel view. Like I want you to move the camera to a position that is none of these 3 cameras, and I want to render an image of the same underlying 3D scene again. Well, how would you go about doing that? You would go about doing that by collecting. You don't know the depth, right? So you don't know where like now you want to render array. So we haven't talked about any of these concepts yet, so I'm trying to explain it anyways. But you want to render array. The array is hitting like some 3D coordinate somewhere, but you don't know that 3D coordinate, so you don't actually know the depth of that point just yet. So you don't know. But the way you're going to do it is you're going to say, I'm going to render that array. I'm going to compute the epipolar lines in each of these images, and then I'm just going to have a neural network look at all the possible candidate colors that could possibly be the correct color. And it turns out that these candidate colors have to lie along the epipolar lines, because along the epipolar line, the correct point has to lie. You just don't know which one. And that's what you're going to solve with like the machine learning hammer. We're going to talk about that in detail later. But just as an example, here's another one. This is, again, the input level inductive biases. Here you can see the epipolar lines. So again, this is the teaser of the paper. So clearly this was important enough to include in the teaser of the paper. Okay, just these two. I thought I had more. Anyways. So you know this now. This is actually what I call it the hacky way, as if that was bad. It's not bad. Totally valid to compute it like that. Go ahead. But we're now going to talk about another way, which turns out is pretty important if you want to use this kind of math to then later derive algorithms to get the camera poles. And like basically what we're doing now is you've noticed I told you, I give you the camera correspondences. We're solving for this. Now I give you 1 point and I give you the camera poles. So I took one of the correspondences away. We're going to find the correspondence. We're going to keep taking assumptions away, and we're going to keep doing math to like figure out the geometry of the system. So we're going to compute more and more things. We're going to at the end compute both the geometry and the camera poles. Right now we're just still computing epipolar lines. Okay, so now we're getting to fundamental and essential matrices, which is basically, for starters, a more elegant formulation of epipolar lines, which in practice means it's a more complicated formulation, I guess. Okay, this always works. Now we're going to talk about a fascinating little topic, which is we need some math that some of you might have not heard about in undergrad, but actually, I don't know. I certainly didn't learn about it in undergrad. I don't think you necessarily have either. But it's the notion of lines and homogeneous coordinates. Who knows about lines and homogeneous coordinates? Nobody. Oh, no, you. Ah, nice. Maybe, yeah, cool. Perfect. One person. So like something. But wait, half of you have heard this lecture before. Not sure how to feel about that one. Anyways, lines and homogeneous coordinates. So this is actually like, it's a very fun little math thing, and I'm actually like, this is something I'm kind of fairly excited about every time. So let's say we have a line in 2D, okay? And we happen to use, for no particular reason, we're going to use the notation as if this was an epipolar line. So like there's E for like epipole and X for like random pixel coordinate. But it could also be X1, X2, it doesn't matter. So now you have a line L. So how can you parameterize lines? Someone give me an example for how you can parameterize a line. Not you. Yes. Origin and direction is one way of parameterizing a line, or like 2 points on the line, right? Okay, so these are all different ways of parameterizing a line. We're now going to talk about a completely new way of parameterizing a line, which is not one of the ones you learned in high school, I guarantee it. Unless you were at a really fancy high school, I don't know. So here is an implicit way of parameterizing a line, right? You can express a line as an equation, which is ax plus by plus c, and all of the points all of the 2D points with coordinates x and y that you stick into this equation that evaluate to 0, those are the points on the line, right? That probably you learned in high school. Okay, good. So here's a funny little thing. Apparently, the line therefore has 3 parameters, which are a, b, and c, right? So it's just 3 parameters a, b, c. And these 3 parameters a, b, c make the line. And you, like, nothing keeps you from writing them in the form of a vector. So you just put them in a column vector and you call it a day. Great. Why would we ever do that? Well, it turns out that if you take a homogeneous coordinate, xy1, for instance, right? Like you take some point, xy1 with it, right? And you now take the dot product with the line, what you get. Let's say that point would lie on the line. What would it be? It would be 0. If the point doesn't lie on the line, what would you get? Huh? Non-zero. Can we be more specific? That's correct. It'll be related to the distance of the point to the line, in fact. So like if this vector here turns out is normalized in a certain way, it'll be exactly the signed distance of the point to the line, which is basically the orthogonal distance of the point to the line, which is a fun little fact, right? So you can do math with 2D lines as if they were vectors. And I told you that homogeneous coordinates are special in a way, and they're not like just a fancy little trick. This is also not a coincidence, and there's a lot more really fancy math, not fancy, but like there's some really cool math that you can do with these lines. So for instance, it turns out if you have 2 points in 2D and they are homogeneous coordinates and you take their cross product, then you get the line that goes through them. This is a fun little fact, for instance. So 2 points, and they are in homogeneous coordinates. You take the cross product, you get the line that goes to the 2 points. How long if you remember in high school, how long did it take you to derive this stuff, right? It always took a few steps. If I give you 2 points in the line, and you'd be like, oh no, here we go, right? And so none of that. You just take the cross product, you're done. It's pretty nice. Unfortunately, it only really works in 2D. In 3D, it gets much more complicated, but in 2D, you can do it. So it turns out that this is really useful, and we're now going to use it to build a little bit more fundamentals. No pun intended, but the fundamentals we're going to build is going to be the fundamental matrix, and then we're going to use that later to give you an idea of how you might actually then solve for the camera poses and stuff of unknown camera systems. Okay, so what is the fundamental matrix? The fundamental matrix is defined as the matrix that goes from a homogeneous pixel coordinate in one camera frame, denoted as x1 tilde here, to the line in the other image coordinate frame. And this is a little crazy, right? Because it is a linear map. It's a matrix that goes from a 3D to a 3D vector, but one of the vectors is a line and one of the vectors is a point. And one of the vectors is a line literally in the sense that we just discussed. So one of the vectors will be a line in the sense that if you take the dot product of a point that lies on the line with the line, it'll give you 0. And the other side is going to be a point in the sense that it's like a point where you append a 1 to a xy1, right? So this is kind of cool. So the fundamental matrix is the matrix that has the property. And for now, you kind of have to believe me that this matrix exists, but you can kind of convince yourself of that fact by just like, thinking about it a little bit and then being like, okay, yeah, it's probably a linear thing, right? The map of this to that is probably a linear map. There's like no nonlinearities involved, so it's probably like a linear thing. So the linear map must exist, so therefore it's a single matrix, like, I don't know, linear operator. So fundamental matrix exists. So this matrix exists, we're going to derive it now. The way we're going to derive it is, more explanation. The fundamental matrix is a 3x3 matrix that encodes epipolar geometry in the sense that we just discussed. Given a point on the image, multiplying it by the fundamental matrix gives us the epipolar line, just as we discussed. And now we're going to, okay, everything that I just said, just in the slide again. I made a slide for it, apparently. Okay, good. So here's the 2 equations that we're going to work off of to derive the fundamental matrix. Equation number 1 is the one that we just introduced. We just said fundamental matrix is defined as this. And then this property is just the property that points that lie on the epipolar line, dot product with the line have to give you 0. Okay. And now we're going to work off of these 2 equations to get the fundamental matrix. So, and this is just shifting around. Equations a little bit. So we're going to take these 2 equations and we can merge them into x2 transpose f x1 tilde, right? And that's because f1 x1 is L2. I mean, I'm sure you can see it. So this must be 0 because it is x2 transposed, like it's x2, which we define to be on the epipolar line, times the epipolar line must be 0. Good. So now some math. We have our baseline again. This is this vector here, and we're going to call that vector t, like small t. This is the vector that connects one camera origin with the other camera origin. And now we're going to introduce these little buggers here, and these are going to be the camera ray directions. And you actually also already know these. These are the intrinsics matrix inverted times x, the local ray direction, and the homogeneous pixel coordinate. We know the equation that takes us from that takes this vector to this vector because we know the offset and we know the rotation between the 2 cameras. So this now is the relative rotation. So this is not part of the cam to world or world to cam matrices. This is just literally, there is a rotation that maps you from O1, like that goes from that orientation to that orientation. It's just some 3x3 rotation matrix, and this is the translation that maps the 2 camera origins onto each other. So these 3 vectors are coplanar in the sense that they all lie in the epipolar plane. If these, knowing that they are coplanar, now we can derive a little trivial-looking constraint, which is that this 3D ray direction, right, this little vector here, dot product with the translation vector with the cross product with this. So what does this give you? It gives you a vector that stands like that, right? So it gives you a vector that is orthogonal to x1 bar, and the dot product of that vector with x1 bar therefore must be 0 because it's orthogonal. Does that make sense? Okay, good. So now we can derive another one of these constraints. Like it's actually similarly straightforward. So this vector here is just another vector that is orthogonal to x1 bar, right? So it's, again, this vector that stands orthogonal on this plane. And now we can just build another trivial expression, which is like x1 bar minus t. So it's just translating x1 by t. And again, this one must be 0 because it's, again, just like an orthogonal dot product of an orthogonal vector to like another vector. So 0 again. And now we just like hit the system with a little math hammer and then dropped out these two things. And now we can use these to get to the expression of the fundamental matrix. So that's what we're going to do now. So we're not just going to work off of these two little equations. We're going to smush them together, hit it, and then out pops the definition for the fundamental matrix. So I don't know that we have to go through these steps one by one, but they are really elementary. There's like nothing fancy in here. It's just like inserting one into the other and reshaping it a little bit. There's just one little trick in here, which you might have not seen before. So the reason, by the way, that we're talking about this, I don't expect you to know this by heart, but these things do pop up from time to time. And then it's important that you know where to look for it. So this is where you look for it. You just go to these slides, and then you look for it in the slides. And then it probably helps if you've heard it before. So there's just one little trick that you can play. Maybe you've seen this before. Who has heard of a cross product matrix before? One person, two person? Okay, a few people. So it turns out if you have a cross product like this one between t and some vector, it turns out you can like be sneaky about it, and instead of like computing this weird cross product, you can write t as a matrix, and then the dot product of that matrix with x computes the same thing as the cross product. This is called the cross product matrix, and it looks like this. So you just take the elements of t and you like scatter them into this matrix in this way. It's this Q-symmetric matrix, which all of this has good reasons. Doesn't matter though, so now you can just write this as like a dot product, and other than that, it's just pushing these two equations into each other. Then you reshape it a little bit, and you can see how you're reshaping it. You're pulling out x2 bar transposed on the left side. You're pulling out x1 bar on the other side. And this expression is starting to look a lot like the expression that we started off with the fundamental matrix. And indeed, the only thing that we might have to do, which you might have overlooked if you were thinking along, is that in the original definition of the fundamental matrix, it was x2 tilde transposed on one side and x1 tilde on the other side. And in between that was the fundamental matrix. That whole thing gave you 0. And these two bars, right, these were just the ray directions. So we had to convert the ray directions into pixel coordinates by just pulling out the intrinsics matrix. So this thing here, again, is the ray direction of this pixel coordinate in camera number 2, ray direction of pixel coordinate number 1, and then there's this thing in between. And so this is now the expression for the fundamental matrix. So this whole term in the middle, that's the fundamental matrix. And so what does that mean? If you ever have the parameters of a set of cameras, like two cameras, and I give you the intrinsic and the extrinsic camera parameters, this is how you can compute the epipolar line. You can just take the fundamental matrix. Now I ask you, what's the epipolar line that corresponds to the pixel coordinate x1? You take it, you compute this fundamental matrix, you take the dot product, and then you get this vector that is just the implicit parameterization of the epipolar line. And then you can convert that into an explicit parameterization if you want to. With implicit, I just mean it's this equation that evaluates to 0, right? Does that make sense? Any questions? Yes? So the two cameras are coplanar. So the cameras don't have to be coplanar. So just for the record, good question. I was confused for a moment. Good question. I'm always afraid of these questions where you don't know the answer right away, and then you're like, oh no, I hope I can. Okay, so if the two cameras don't have to be coplanar. So the cameras, in fact, the cameras you see here, they are converging, right? They're not actually coplanar. It's just that if you pick any point in 3D, you can like, that point, you can connect it to the two origins of the two cameras, and that always forms a plane, and that's always the epipolar plane. So it's coplanar in that sense. Yes? Yeah. I haven't worked with differential equations for a while, so I would know. Can anyone, like actually, no, I'm probably not going to figure it out right now. So probably not. I haven't heard of them in the same context, for sure. Yeah. Any other questions? Yes. Aha, great, yeah. So R, this is actually, I think, some feedback that I will take away from this lecture, that this is something I should introduce before, because, so R, what is R? So we said, when we started out with this, right, we said that we would know, okay, I'm gonna always turn everybody. Anyways, okay, so we have like, yeah, we're gonna draw it in 2D. So we have camera 1 and we have camera 2, right? And I told you up front that we know the P1, P2 matrices for these two cameras, right? So like I said, P1 and P2. This is terrible chalk. It's this chalk. Oh, okay. Also, my handwriting sucks, so I apologize if you can't read it. I'll try my best. So this is P1, this is P2. So what is P1? Right, it has two components, right? One is K, K1, exactly, K1, right? And the other one was this matrix, the world to cam matrix. So it was like W to cam, right? So this is the matrix P. And then here we have the same. We have K2, the intrinsics matrix, and then we have this world to cam matrix here. I should say C2, C1. And now these two matrices, respectively, right, they just have this component R. And now this is a slide. They have one rotation matrix part, and they have one translation part, right? We're just going to denote it like this now. R2, T2, 1, 0, right? And now the trick is just that both of these give you the coordinates of these two cameras relative to some world coordinate frame, right? Like in this case, it's all 2D, right? Like I haven't assumed any coordinate. So maybe the coordinate frame, I don't know, the coordinate frame is here. And then in fact, this is one coordinate frame of this camera. This is one coordinate frame for the other camera, right? So rotation 1 is just the rotation 2. Rotation 1 is just this rotation here, right? Rotation 2 is just this rotation here, right? And then you have the two translations of the camera origins relative to this world coordinate frame. And now all that this rotation vector here is basically a function of these two matrices. It's basically like it's the rotation of this frame to this frame. And you can calculate it as a function of these two. I'm not like before I mess it up, I won't do it now. But like basically I think it's probably this matrix inverse times this one. But it's like something you always get confused about. But like basically you compute this R as a function of like camera world to cam matrix 2 inverse times the other one. And then you get both the translation and the rotation out. And this is a great point for the next lecture. Next time I give this lecture, I'll put it on the slide. Does that make sense? Any other questions? Great. Beautiful. Then we are done with the fundamental matrix. Cool. Fundamental matrix. Yeah, so now you know how to compute it. Now you know how to compute epipolar lines. And again, the Hacky way always works. And the Hacky way, in fact, also has a benefit, which actually David can talk about more in his office hour if he wants to. But there is one benefit of the Hacky way of doing this, which is last time we talked about vanishing points. Do you remember talking about vanishing points last time? So imagine you have two cameras, and they're kind of like close together, right? Then what happens is we discussed last time that if there is a ray that emanates one of the cameras, then that ray, as it goes to infinity, it'll converge to one pixel coordinate in the other camera, right? Like it's just this example of you like standing on the rails of like, and you're looking into infinity, right? The lines converge. So what actually happens is that the epipole, it might lie at infinity, but not the epipole, but the camera, as this ray goes to infinity, it might converge to some point on this image plane. It might not go any further. Does that make sense? Right? Because it might converge to this vanishing point, and then it's there. And so actually, you shouldn't look any further than that point. Like if you're searching for correspondence, you don't have to look any further than that point, right? Because if the ray goes to infinity, the furthest you have to look on the image plane is like there, and not any further. Does that make sense? Yeah, good. So this approach has some benefit because you could explicitly compute this vanishing point. Does that sound good, David? Yes, good. Didn't explain anything wrong. Good. So this always works. It has some benefits. But we didn't derive the fundamental matrix for nothing, because now we're going to solve the problem of the camera poses not being known. You know neither P1 nor P2, and now you want to compute the camera poses. this is now starting to get fairly difficult. So like up until now, like you can, like this is all easy. Now it starts actually becoming like kind of a little bit involved. And it's kind of fun. So now we're going to briefly talk about point correspondences. So in fact, we're not talking much about this because I don't think there's really all that much to talk about. So far, we always assumed that there's some kind of algorithm to like tell you which 2 points on the 2 images belong to each other, right? Like which two pixels map to the same 3D point. Like for instance, you find this correspondence or you find this correspondence. In fact, this is not an easy problem in itself, and there were algorithms that were written just to find these correspondences. And the way these work is by, we already briefly hinted about it. The way these work is that you pick, for every pixel in this image, you'll compute a descriptor. And that descriptor might be like really basic. The descriptor might be the color of the pixel, right? And then you're going to compare that descriptor to every other pixel in the other image, right? And then you can just see which pixel matches best. And then you say, this is my correspondence, right? That's the basic idea of finding correspondences. As we discussed with colors, it really doesn't work because colors are like not represented. I mean, even in this room, right? All the walls have the same color. What you're going to find? Nothing. Okay, good. So it turns out that the way you compute correspondences, you get really smart about these descriptors. So you don't, for starters, you don't like take every pixel from this image and try to find a correspondence in the other image, but instead you only pick pixels in this image that you believe are going to be like very informative, like that you actually can find in the other image. And intuitively, what will be in this image? What do you think? For which pixels of this image do you think it's going to be easiest to find the correspondence in the other image? Yeah.
Sharp edges.
Right. Sharp edges, corners. Right. That's easy. Right. In fact, that's why we picked this one. Right. Like you can immediately find this one. It's very very informative if you find edges. And so it turns out that these descriptors, like SIFT, the way they work is they basically work by identifying local geometry that is likely to be robust to like lighting changes and that you're likely going to easily find in the other image. And they work by, for instance, computing like gradients in the image and then doing a histogram of gradients or whatever. But we're not going to talk about it too much. But the basic idea is you pick information-rich pixels in this image, you compare them to all the pixels at the other images, and if you do a good job at that, you can find correspondences. Does that make sense? Excellent. That's all we're going to talk about. There's lots of other tricks you have to play because many of these correspondences, even if you're really good at building your descriptors, many of the correspondences will be trash, and you have to throw them away somehow. And that's done with algorithms like RANSAC. Yeah, but I'm not talking about it. Okay, so let's assume you have found these correspondences. Then there was this paper earlier that we briefly saw, which had this 8-point algorithm in its title. What is the 8-point algorithm? The 8-point algorithm is exactly the way how you find the poses of two cameras if you only have correspondences in pixel land. Okay, so that's the name of the 8-point algorithm. And the 8-point algorithm is so called because it requires 8 points to get the camera poses. Let's go through it. And now that's what we did all the shenanigans of the fundamental matrix for. It would be really hard to do this without the fundamental matrix. The idea is going to be that we're going to leverage this epipolar constraint to estimate the fundamental matrix from correspondences. So now it is important to note that the fundamental matrix also has the intrinsics matrix in it. So we can compute the fundamental matrix, but that doesn't mean we have figured out the relative pose of the two cameras yet, because there's still the intrinsics parameters. We're going to deal with that later. Okay, so we're going to do that. The way we're going to do that is we just write this whole thing out as one big linear system. So I hope this looks confusing, but it's really not that confusing. It's just you multiply this thing out. And if you multiply it out, you get something that looks like this. There's these cross terms, x1, x2, x1, y2, x1, y, x2, la-di-da. And then here, there's all of the elements of the matrix, and that whole thing should be 0. Does that make sense? So it's just one big linear system. And now we can write this linear system like this. So the thing on the left, we're going to call W. The thing on the right, F, we're going to call F. And it turns out that if you take 8 points, so like you take eight of these constraints, then you can solve for this. Matrix F up to scale by solving a linear system. So you need 8 points. You put it into a linear system. You can solve for F up to scale. And then there's like much more detail here than we have time to go into this lecture. I just want you to have heard about it. So we can determine this f up to scale. Note, however, what is f up to scale? It means you have all the elements of the fundamental matrix, f11, f12, f23, and so on and so forth. But f is this whole term here. So f is a combination of the intrinsics parameters and the camera poses, right? So just for the record, if you were perfectly successful at solving for f, then you would have the elements of this matrix as well, right? This is what f is. And now, finally, if you knew the intrinsics parameters up front, then you would have the pose between the two cameras. Does that make sense? No? Kind of? Okay, so if it doesn't make sense, then who has a question? So basically, let me walk through it one more time, just to get the intuition. So we start with this little thing up there, right? So this makes sense. Does this equation make sense? Yeah. So this also makes sense, I guess, right? You could just write it out, big thing. Yeah.
Is the row version little f?
Yes, good point. Thank you. Great first confusion. So in fact, yes, the f is this column of f's. That's the small f in the next slide. That small f. Does that make sense? Okay, and the W, yeah, actually this is good. So I'm sorry, I'm collecting feedback for the next time I give this lecture. So what I'm hearing is that's absolutely not obvious. So f, small f, that's this vector here. And then this W, as I mentioned, there's a reason why it's 8 points. But basically you take eight correspondences, like eight pairs of x2 and x1, and then you get 8 of these row vectors. Does that make sense, right? And so now W is you stack these 8. So it gives you an 8 by 9 matrix. So this is 9 elements, right? So you stack 8 of them, it gives you an 8 by 9 matrix. Does that make sense? And now it's a linear system, and when you solve for the null space of W with if you solve for the null space of W, then you can get the elements of this matrix F. Okay. And now so what I want you to hear from this is if I have correspondences, I can solve for f. That's what I want you to remember. Okay? And I want you to remember that that's called the 8-point algorithm. And then the other thing that I want you to remember is that when you then have the intrinsics parameters, then you can get the relative pose between these two cameras. So now you might ask, how do you get the intrinsics parameters? It turns out we're going to talk, there's several ways of doing it, but it turns out the intrinsics parameters are much easier to get than the camera poses. So in fact, there's very standard ways of getting the intrinsics parameters of a camera. If I give you a camera, you open OpenCV. Who knows OpenCV? Great, okay, hopefully almost everyone. So if you take OpenCV, there's literally a thing called calibrate camera. And you have to print out a checkerboard, and you point the camera at the checkerboard, and out pops the intrinsics parameters of the camera. So getting the intrinsics parameters of the camera is relatively easy. But now, trust me, if you build a system, like where you have 2 cameras and you make them point at your robot, and you're like, great, here's my system. Now I want to get the pose between the 2 cameras. How are you going to do that? You're not going to get very far if you try doing it with like a measurement tape and like something to measure angles. That's not going to happen. Although I've never tried. Maybe someone has tried. I imagine that would be extremely hard. But this is like the general idea of how you might go about doing that. Of course, there's also software packages for that, so you're never going to do this yourself. But you know how it works. Great. So now you know what the 8-point algorithm is. And the 8-point algorithm was, for instance, used in this paper here for relative pose prediction. So this is a deep neural network learning paper. So the point of this paper was I give you 2 images, and I want you to predict the relative pose between these 2 images, an old and important problem. So you want to get the relative pose. And now what this paper did is something that many computer vision researchers here at MIT like very much, this general idea of, okay, don't learn things that you know already. Right? So you could, of course, just build a big data set, and then you just build like some black box neural network, and you stuff all of these images, always pairs of images in, and then you like make it predict the pose, and you hit it until it works. But that turns out it doesn't work that well if your data set is small, and it's really hard to collect this data set in the first place. So you might want to be efficient about the data. So it turns out if you make your neural network simulate a part of this algorithm, then you will need much less data, and it's going to work much better. So that's the point of this paper. So knowing about this 8-point algorithm in this case helped them get a much better performance for camera pose estimation. So this remains useful even in deep learning. Great. So things we didn't talk about, really. We didn't talk about correspondences. We didn't talk about RANSAC. We didn't talk about camera calibration. But I think that's fine, because now what we're going to talk about is bundle adjustment. So we talked about all of the stuff when in reality none of you will ever use this, but it's good and it's still important to learn about it because many ideas, as you just saw, might be inspired by that. So if you ever build deep learning architectures, then maybe you think back to this and you're like, oh, maybe this is how I could do it. But now this is how you actually get camera positions today and in the real world. So this is how everyone does it with bundle adjustment. And the idea of bundle adjustment is, what if we in fact have lots of views? So we don't have just so far, we've always looked at these stereo systems. Imagine I have 1 million, okay, maybe not, like 1,000 camera pictures of some 3D scene, and I want to reconstruct the 3D scene. And this is a very common case, in fact. Think about, for instance, you want to sell your apartment. And to sell your apartment, you want to reconstruct a walkthrough, like a 3D walkthrough of your apartment. How are you going to do that? You're going to get your phone and you're going to like wave it around like a map. In reality, you pay someone to do that. But in principle, now today, there's an app, actually, that you can like wave your phone around and then they reconstruct it. So this is what bundle adjustment was originally motivated by. I already showed you this picture. Yeah, this is phototourism. And this is exactly what this paper did. So again, there is a whole course you can take on how bundle adjustment works. So this is just going to be the idea of how it works. But I hope now actually we can like go through this and all of the words make sense to you. So the first thing, let's just go through these one by one. So there's 3 lines here. The first line says, let capital pi equal the set of little pi i's denote the n cameras, including the intrinsic and extrinsic parameters. This is a notation you will see often. I actually don't know why people started calling it pi, but oftentimes the projection operator. So this, right? We had this matrix P that if you multiply it with the 3D world coordinate in homogeneous coordinates would give you the pixel coordinate in homogeneous coordinates. Remember? So oftentimes this operator is denoted as pi. So oftentimes people write like x equals pi of x. And then sometimes they say this parameter is like and depending on how you want to formulate it, you could say this takes as input the camera parameters, or in this case, they say each camera basically has its own pi I, which is the operator that projects from 3D coordinates to 2D coordinates. So this is basically, if you wish, the set of camera matrices P, right? Okay, good. Then the second line is let xw denote the set of 3D points in world coordinates. So this is the thing that we like neither of these things are known. So this is, we're just like setting up the problem. And then this last thing, that is actually the thing that is known. Let xs denote the image observations in all I cameras. So this is now the set of 2D correspondences. So like this is basically, we have an index p and we have an index I. I is the camera index and p is the index of like a correspondence. So you have one correspondence in all the camera frames. You have another correspondence in all the camera frames. Does that make sense? Yeah, good. Okay, some nods. Good. So bundle adjustment now just is actually, it looks very similar to the triangulation thing that we discussed earlier. Yeah, right. We've actually already seen this pi in this triangulation thing, right? Bundle adjustment is like, the idea seems intriguingly simple. We're just going to solve this big optimization problem. And this optimization problem is going to be over the set of pi, which is basically just the set of all camera parameters, right? So this is just these small pi i's. So we are saying solve for all the camera parameters while also solving for the 3D coordinates of all of the points. And the way we're going to do that is we're just going to pick a correspondence, right? And we have like a correspondence in each. Next, okay. So right, so like let's say we have these two. These are 2 views, right? So like this is camera number 0, this is camera number 1, and there might be more. And now you have like this at this point, right? So this would be x 0, right? So x0, like let's say 1. I now see the x is not ideal because okay, point. This here would be x1, 1. Right, so this is the 0th camera, this is the first camera, and this is like the index for the correspondence. So this is the correspondence that we have. And now there is a 3D coordinate, which is this point x1 world. So this is in world coordinates now. And now what we're doing is we're randomly initializing the 3D point because we don't know it. Then we're going to project it onto all of these cameras. So let's say we randomly initialize it. We project it with the projection matrix that we also don't know. So in the beginning, we don't know anything. We randomly initialize it. We project this point here. Maybe it gives us, I don't know what else to draw. I don't know. I'm going to we have colors? No. Okay, I'm going to draw an X. I'm sorry. X and X is a little confusing. I'm going to draw an X for the point. I'm going to make a circle around it. That's going to totally fix it. So X, circle. This is going to be this projection, and this is going to be this projection. And now we say, please minimize these distances. So iterate through all of my cameras, right? And we're just minimizing the set of the distances. And we are jointly optimizing the 3D point and the projection matrices. And so that seems intriguingly simple. If you try to do this with gradient descent, it's not going to do anything. It's just going to sit there and do nothing, right? Because this is an extremely non-convex optimization problem. Like, in fact, and you can think about why that might be the case. But like basically, if you just try to solve this with gradient descent, it's not going to do anything, right? And this is now what people have done 30 years of research over, or like call it 40 years of research. So like a lot of research has gone into how to do this, which is why this kind of works today. And when I say it kind of works, it works in like 90% of the cases. I already mentioned this in the very first lecture. I told you about this algorithm that people have been using for 30 years, and it kind of works. Great. So the thing that I just drew, I have it again on the slide. But like, does this general idea make sense? So the free parameters of the system are the 3D coordinates, which you randomly initialize, and the projection, the camera pose plus the camera intrinsic parameters, and you're jointly optimizing the camera intrinsic parameters, extrinsic parameters, and the positions of the 3D points in one big optimization problem. And this is called bundle adjustment. Okay, good. So if you do this again and you try to solve this with gradient descent, nothing happens. It's super non-convex. A good initialization is crucial to avoid getting trapped in bad local minima. So now people figured this all out. Took very long. So the way this is done in practice is called incremental bundle adjustment. And now this is a very fancy word, but now I think you can all put it together. What incremental bundle adjustment means is you like, let's say you have a video. So if you have a video, then you kind of know that the frames are in order. So you know like the frames that are in order, like next to each other, consecutive, these are probably the frames that kind of look at the same stuff, right? Okay, good. Let's start with that. You start with the first two frames. And then, in fact, you do all of this 8-point algorithm shenanigans that we just talked about. So you take these two frames and you start with doing this 8-point algorithm stuff. And you start trying to get a good initial estimate for the projection matrix and for like the intrinsic parameters and all of the stuff. Ideally, maybe you have a calibrated camera, then you don't have to solve for the intrinsic parameters, good for you. Then you just have to solve for the pose. But then you can basically solve for a rough first initial estimate. And then you do one round of this global optimization, okay? And then you add a camera. And then like you first do like, you take the next frame and you do the 8-point algorithm thing again, you get a good estimate, then you do it again. And so so you keep on adding frames and you keep on adding frames with a reasonable initialization, and then you keep on running this optimization problem. Does that kind of make sense? Cool. Yes? Ooh, good question. It runs only on 2 cameras, I think. I think there is a generalization though, which is I think there is generalizations of it for cameras and for systems with 3 cameras, but I don't think anyone uses this. I think in practice it's like you do it incrementally, but I'm not 100% certain. Right, the 8-point algorithm just gives, yeah, great question. So the 8-point algorithm, yeah, a great question. So the 8-point algorithm, as we discussed it, right, actually just gives you the fundamental matrix, which is just the intrinsics and the extrinsics. Then you still don't have the 3D coordinates that belong to the correspondences. So however, we know how to solve for the 3D points from if you have the pose and the correspondence. That's the triangulation thing, right? So it's like this, and there's lots of steps we skipped. So like we just said like, now you can solve this by finding the null space of this, and then then it's only up to scale. You need like another constraint and like la-di-da. Read the Wikipedia article. But I'm sure you can understand it, like if you want to get into it from today's lecture, but it's not straightforward. But yeah, basically you keep on adding and you keep on doing these like heuristic solves, and then you like add stuff to it, and then you do this global solve again and again and again. Any other questions? Yes?
How do you determine like how to use this algorithm?
Yes. Sorry, I don't mean you guess. I mean like you guess, more or less. It's like all heuristic. Like all of this stuff is like engineered to death, and it's all heuristic. So the only reason why it works is because people like hit it with like the engineering hammer until it kind of submitted. But there's like no. Good question. Can you cross-validate it? So first of all, in principle, the more views you have, the better. Like the more views shouldn't make the problem harder. So in practice, I think you use all the views always. You just use all the views that you have. But it is a fair question. I'm sure there are papers written about that exact question that you just asked. I'm sure there's someone who's been like, turns out if we only use the subset with this heuristic, we can do better. And my guess would be that the flavor of these papers is very similar to the flavor of many deep learning papers today, which is basically it was kind of like it seemed an interesting problem at the time, but it's like very specific to this particular way of solving the problem. Any other questions? Okay, so who has run COMAP before? Okay, so I wonder if we, I wonder actually maybe in the next time I give this lecture, we're going to do an interactive demo, which may or may not fail. I guess it takes too long, unfortunately. But I encourage all of you to go home, to whip out your iPhone or your Android phone, whatever, take a video, okay? Or like take a bunch of pictures. And then you download COMAP, which is a piece of C++ code. I've been told it's the most beautiful C++ code people can possibly write. It's very well optimized. It's an amazing piece of software. It's open source, completely free to use. And then you can run it on your set of pictures. And then with like a 90% probability, you're going to get out the camera poses and the point cloud of your scene. And it's going to be very rewarding, maybe. Yeah, so that's an unofficial homework. Maybe we can, I don't know, maybe we could make that part of the, like maybe that's like extra credit for the next homework. You have to submit like images and pictures of your point clouds or something. You were never able to get it running?
I tried during the computer vision class. Never ran.
Oh no. What computer do you? See, this is, it's kind of, okay. That's funny, that's sad. Okay. Well, yeah, it is a pain because, I don't know, I don't think you have to compile it. Are there binaries or I think you have to compile it?
I'll try again.
Okay, try again. Does it run on your Mac, David? Have you ever run it on your Mac? But you've run it on Linux. It's probably done for Linux. It's probably written for, so if you have a Linux PC, it should run. It shouldn't be that complicated. If you have a Mac, I don't know. You say, you runs on Windows as well. Yeah, cool, good. So yeah, that's it. There's also commercial versions of this available. Like I don't know their names, but we don't like them, so we do open source. Good. Computationally binding, super expensive. Here's a fun fact. One of the common data sets that we use in our research is called Co3D, Common Objects in 3D, and it is a data set that Meta published. They just paid a bunch of people to like go around fire hydrants and other objects with their phones, and they take videos. And then they had to compute, to make it useful for the research community, they had to compute the camera parameters. How did they do it? They do it with bundle adjustment. And it took 5 GPU years. It took 5 years of GPU compute to run this algorithm to get the camera poses for this data set. So I know it's kind of comical. Not their fault, obviously. It's a great data set. And news, like, in addition to that, about half of the objects have poor poses. So half the time it kind of doesn't work. So, it's kind of crazy, but this is the status of the 3D computer vision. This is the status of this particular kind of problem. When I started my PhD, everyone was like, oh, I was really excited about this problem, and we're going to talk about the paper that got me into 3D computer vision in the next lecture. That got me most excited is actually also one of Noah's paper. He's also on that paper. I was really excited about the idea of building neural networks that solve for camera poses and that learn to reconstruct the geometry. Like, it turns out that's what I ended up doing. But when I started my PhD, everyone was like, no, like structure for motion is solved. You're wasting your time. And it's really interesting because very clearly structure for motion is not solved in the way that I can't take an arbitrary video right now and put it into COMAP and it's going to work. If anything, like, an assumption that we haven't talked about, this assumes that nothing moves. This assumes that everything in the scene is like as static as like a building, right? If lots of stuff in your scene moves, it breaks. It just fails. It doesn't do anything. And there's like a bunch of papers that try to fix this with like a variety of involvement, but it literally doesn't work. But at the time, I was like, okay, I guess not worth my time. Now it turns out we work on this stuff, and I'm very excited about that. But the thing that people mean when they say something is solved, and I think this is something to keep in mind, the thing that people often mean is that so many people have worked on this, and this field is formalized to a fault. Like when you read these papers, all of this formalism that we just went through, this is one of the best formalized fields in computer vision. And what they really mean is so many people have put their time into like incrementally optimizing this algorithm. If your approach involves incrementally improving on this algorithm, you're wasting your time. And that, I think, is true. But it turns out we need actually something completely new because this algorithm clearly isn't cutting it. So we need something completely new. And that is definitely still unsolved. Very exciting. Cool. Results and applications. So here's like an example. This is CallMap. You can like run around a city and then you take videos, and half of the time it gives you like these cool point clouds. Or you can then, as you might imagine, this optimization problem is very expensive. The more points you have, the more expensive, right? Because like the more points you have, like just get much more. Okay, so this is a problem if you went dense point clouds at the end of it. So if you went dense point clouds, then you would have to optimize over like millions of points. Like this point cloud probably has like, I don't know, 10,000 or 20,000 points. Or I don't know, maybe even more, I don't know. So lots of points, that would be very expensive. So instead what you do, just to give you an idea of the degree of like steps involved, instead what you do is you start with a set of sparse correspondences. So you have very few correspondences in each image. Then you solve for the poses and for the 3D coordinates of the small set of points. Then once you are pretty certain that your poses are correct, then you add a bunch of points, and then it turns out you can do something closer to triangulation, because then you don't have to solve for the poses anymore, because you have the poses already. Then you do triangulation to make the point cloud dense. And this is then called dense multiview stereo. So like the moment that you have the poses, the problem is reduced to something that's called multiview stereo, which is basically a big triangulation problem. Cool. Phototourism, like this blew many people away back at the time. This was SIGGRAPH 2006. So SIGGRAPH is an interesting conference. It like went through a time of being a hub for like the 3D computer vision community. Then in recent years, because SIGGRAPH kind of slept through the whole deep learning stuff, like people didn't send their deep learning papers there, but now again people are sending their deep learning papers there. So SIGGRAPH is a conference that is like a hub for these kinds of papers, and SIGGRAPH, this paper was published at SIGGRAPH back in the day. And then this is PTAN. This is a SLAM algorithm, which is also a form of, so this is a real-time version. And when I say real-time, I mean it works in real time. This is from 2007, okay? So here you can see an algorithm that only does sparse correspondences running in real time on this video. And yeah, like, I mean, this is pretty cute. So you can like run it. Here you see the correspondences. What you just saw were the correspondences. Then it did a little solve for the 3D coordinates, and then you can like fit a plane to it, and then you can make stuff run around on it. So this was 2007. So pretty cool. And I think this was in Japan, and the authors of the paper just like collected these videos on their way to the conference. It's kind of cute. This is also how my bachelor thesis was about a SLAM algorithm as well, which was called LSD SLAM. I didn't contribute to the algorithm at all. All my bachelor thesis was about is like I take these point clouds and then I find the plane that is like the ground plane. I had no clue about computer vision back in the day, and it wasn't very, like looking back, it wasn't very groundbreaking, but you know. Okay, so yeah, so here you can basically see them like tracking correspondences, then solving for the 3D, and then you can like play stuff on it. It's kind of cool. Yeah, and you can see how, like now, of course, like if you look at the Vision Pro demo, right, like the stuff people have been working on for like a long time. So it's kind of cool. This is kind of working now. Okay, anyways, what has changed since deep learning? Long story short, the only thing that I know that has made its way into mainstream structure for motion and SLAM that comes from deep learning is a paper called SuperGLUE, which is very recent, and SuperGLUE proposes a way of like learning these descriptors, which we didn't talk about too much, but what they basically do is they train a neural network in like a cool way, in an involved way. They train a neural network to tell you which points are likely going to be good correspondences, or like good descriptors that you can look for correspondences for, and then they train that. And now I think in CallMap you can make a flag that says use SuperGLUE, and then sometimes it works better, and sometimes it works worse. But this is a cool little paper. So like this is a paper from 2019. And it's like it's pretty cute. So you can imagine that it's like fairly involved. They have like graph neural networks in there because the correspondences are discrete set of points and whatnot, but they do a whole thing. You can take a look. So other than that, this we're going to talk about next time. So this paper was the guy who one of the authors just defended his thesis today. So we're going to talk about this later in the course, but there is now alternative, people are thinking about alternative ways of doing this, and we're going to talk about later in the course, but these are like far away from mainstream. No one actually uses this for the first stage of like getting the camera poses today, although you now use it to get like slightly better camera poses, but we're going to talk about it later. So honestly, what has changed since deep learning is like nothing. Since deep learning, the stuff that you just saw from 2007, it's basically like the algorithms have improved, like slightly different optimizers, like more robust, all that stuff, but fundamentally still the same stuff as in 2007. And in fact, COMAP now is, when was COMAP published? It's 2016, I think. So 2016, that's already 8 years ago. COMAP is the thing that everyone uses. So at least since 8 years, nothing has happened. Definitely nothing has happened in 8 years. And actually, the author who wrote the COMAP paper before that wrote like 3 other papers that are like building up to COMAP. And like that's basically what everyone's using still today. And it doesn't work that well. So it's like, I mean, it works amazingly, huge fan, but like it doesn't solve the problem. So like lots of room for improvement. Okay. I think this is, and then, so I mentioned briefly that my research group is looking into alternative ways of solving this problem. So this is a recent paper that we wrote, but maybe don't go read it just yet because we're going to discuss it in class. You can go read it, then you maybe have interesting questions. But this paper is called FlowCam. It's about the same problem. It's about, I give you videos and now you're solving for the pose of the underlying 3D scene while also solving for the geometry of the scene. So this is an active area of research, and my hope is that in the next 2 or 3 years we can build a new generation of these algorithms. And hopefully the next time I give this lecture, I'll tell you that we don't need the other stuff anymore. That would be cool. That's the end of the lecture. By now you should know, if I give you this video, what to do with it, and which is stick it into comment. But long-winded way of saying that. Thanks for coming. And starting from next week on Thursday, no class next Tuesday. Next week, Thursday, we're going to talk about only deep learning, just deep learning then. Thank you.